Hello everyone, welcome to today's webinar, Getting Started with AWS IoT. Before we begin, I would like to walk the audience through a few items. On your screen, you can see a Q&A pod. Please submit your questions for our presenter at any time. We have a group of Q&A moderators who will answer your questions throughout this presentation. At the end, there will be 3 poll questions preceding live Q&A. Today's webcast is being recorded. We will send you a follow-up email with the recording URL as well as a link to the presentation deck. And again, welcome to today's webinar, Getting Started with AWS IoT. Our presenter is Kyle Roth, Director of AWS IoT. Before Amazon, he was the founder and the CEO of Telemetry, an Internet of Things startup that was acquired by AWS in March 2015. Kyle is also the author of numerous technical books, including Professional iOS Augmented Reality. He has 15 years of experience in IoT space and has worked in various industries, including power, retail, and financial. He studied mathematics at University of New Mexico. So today we also have a group of 7 moderators from Solutions Architect, Product Management, and the Biz Dev team. So if you have any questions, feel free to submit. We will answer them while they come in. And we'll also flag a few for Kyle to address in the end. So Kyle, welcome, and I'll pass the floor to you.
Hi, this is Kyle Roach. I'm the General Manager of AWS IoT. So today we're going to discuss the AWS IoT service and its features and walk through a couple of the key components of the Getting Started experience. So we only have an hour. We're going to try to put a lot of content into this. So we're going to skip a little bit of the marketing setup. So basically things are getting connected. On one hand, you see a new Kickstarter project daily about the latest connected product idea. On the other hand, traditional global brands like John Deere, BMW, Philips, Sonos are connecting their products to the cloud and extracting all kinds of new value for their customers. So this trend isn't slowing. In fact, it's just getting started. So that's why we built AWS IoT. It's a fully managed service for your connected devices. You never have to worry about provisioning capacity or managing your shards. It'll scale with your business from your first device to your millionth device. AWS IoT is built for bidirectional, long-lived connections. AWS IoT provides simple integration patterns to the rest of AWS so you can build your business applications around your connected products just like you do today. So this webinar is going to move at a fairly quick pace. So I want to mention that all of the AWS IoT components are described in a fully interactive tutorial in the web service console. So if you missed something today, you can walk through that experience as well. All right, so let's start with a logical overview of the components of AWS IoT. In the center is the Device Gateway. The Device Gateway is an elastically scalable connection layer for devices. It's designed to hold long-lived connections and behave as a compliant messaging broker. So right now, the Device Gateway supports HTTP and MQTT. We announced WebSocket support on stage at reInvent, and that's coming later this year. The idea is that the gateway can continue to evolve as standards in the industry become more prevalent. So these protocols are all designed around a publish-subscribe pattern. A single message can have multiple subscribers, giving you an easy way to communicate with one device or your entire fleet. So on the left side of the architecture, you can see the Device SDK. The Device SDK is currently available in C and Node, and there's a build for Arduino. This helps you easily connect your hardware device or your mobile application to the cloud. So the SDK launched with an ecosystem of hardware partners that are offering development kits specifically geared towards AWS IoT. So I want to point out that the SDK is totally optional. Because we're embracing open standards like HTTP, MQTT, and WebSockets, your devices can talk to AWS IoT with any standard library that supports our security schemes. So devices are a little bit noisy. So consider a temperature taking samples every few seconds. Most of this data is noise. Every once in a while there's a change or a signal, and that's what you want your application or analytics to capture. The rules engine in the top right here allows you to define conditions that allow AWS IoT to measure and detect signals. So when a signal is detected, you can act on it. The rules engine provides dozens of string manipulation functions, numeric functions, and even integrations in the other services within AWS. So we'll go through some more advanced examples later in the session. In the bottom right, we have the device shadow. This is a key concept that we introduced specifically for connected product operators. It's an abstraction layer between the world of web and mobile development and the connected product. Specifically, the shadow acts as a logical interface for your physical device. It also acts as a state machine for your device in times where it might be offline are unavailable to the application. We'll also talk about that later in this session. So lastly, we need a place to store metadata about all these different devices. The registry handles that. So we're going to start with a deeper dive with the registry, as that's where we're defining our devices. So the registry, like I said, is a place for you to identify and manage your connected devices. In the console, you can see the registry attributes for any of the things by selecting the thing in the resources grid and navigating to the detail page. In this example, I'm showing a serial number, an ASIN for a product code, and maybe an EIN for this particular device. So some customers are using the registry to store links to service documentation for field technicians. Others are using it to track firmware versions and capabilities of the device. Everything in the registry is also available through the CLI. You can see the list things CLI command can pull attributes of the same device. So defining the device is totally optional. This is not a provisioning exercise that's required by any means. It's a way to organize your fleet, and if it makes sense for your business, store that type of metadata. So if you're a maker and you're just looking to explore the service, you can skip these steps and just get started with connections. So whether you listed the products in the registry or not, you'll eventually want to connect them. So as I mentioned earlier, AWS IoT requires mutual authentication to connect a device to the service. Mutual auth is a little bit different from TLS on a website. For example, consider the case where humans browsing to a secure site on the web. That person connects to the site presents a certificate, and this is totally public data. The site also has a private key that's never shared. So there's a challenge response sequence on the site that the site goes through to prove that he has the private key in his possession, so the browser knows that that pipe is secure. The main thing here is that the connection is secure, but it's still anonymous. That's why most secure sites require you to still sign in. So with devices, this doesn't work quite as well. Device connects, the service presents a certificate. The service still cryptographically proves it's in possession of the private key, but anonymous isn't really okay for the device. So how does the cloud or your app know that the device is also who it says it is? So we need a way to identify and secure this connection in both directions. So that's why we chose to require TLS mutual authentication. We force the device to go through the same sequence, but in the other direction. The device is in possession of a key as well, and it proves to the service that it has that in the same way. So we have the same secure connection, but now both parties have proven who they are. They are who they claim to be. So here's a summary of the changes that we've made to the AWS IoT security scheme in context of AWS and what we've included for connected devices. You can read more about these in the developer guide. So I mentioned rules a few times already. You might wonder how we secure rules in context of this mutual authentication. Rules are invoked as a service principal within context of your account. So you authorize the rules engine to only execute actions that are within your security profile. If you've ever worked with IAM rules or policies, this should look very familiar. You're in complete control of what the rules engine is allowed to manage and what actions it can perform. So in this screen, we're showing the IAM console with a policy document that allows the service principal for the rules engine to execute functions on Dynamo and Lambda. So we're going to switch to a quick demo showing how we create keys and certificates from the AWS CLI. So all the commands I'm going to run through today are also available on GitHub Gist. The URL is gist.github.com/Kyle Roche, KYLEROCHE. So if you want to follow along, you can use that to cut and paste. So we've created an easy command that creates both the keys and the certificate over a secure connection using the AWS CLI, and then allows you to copy that. Sorry, let me just clear this one more time. Allows you to copy this to the firmware of the device. So in this command, I'm using create keys and certificates. I'm going to set it as active. I'm going to take the output, capture the private key, and I'm going to store that to a file. So now I have my private key and I have my global root cert. The global root certificate is available from the website as well. So now from here, I can list the different certificates and capture the last one that was created. I'm listing in ascending order, so I can quickly and easily find the last one that I added through the CLI. Now I'm going to describe this last certificate and capture also the certificate text and put this in the text file on my machine. So now I'll have both the private key, which I captured over the wire in the first command, plus the certificate, and I'll have everything I need to identify and secure my connection. So now I can have you can see I have my global root cert, I have my private key, and then I have my certificate file. And so that's it. With a couple quick commands, I can create a certificate, capture my private key, store it to my device, and be ready for a connection. So we have the certificates we need to connect. So let's revisit the device gateway. This is the component that we'll be interfacing with for messaging. So to refresh, the device gateway is responsible for the long-lived connections to the cloud and is currently able to speak MQTT and HTTP. I mentioned this earlier, but it's important enough to reiterate. The device gateway is based on open standards, so any compliant open source client, in our example we'll be showing the open source Mosquito client, should be able to connect and send messages to AWS IoT. So the device gateway is designed around a topic-based architecture. Topics are hierarchical categories of your device data. When a device or application connects, it subscribes to a set of topics. Any messages published over those topics are delivered to all connected subscribers. So depending on your persistence choices, the messages can also be queued for an offline subscriber until reconnection. So in the illustration here, the control unit is publishing a command instructing this connected light bulb to switch its color to red. The light is a subscriber on this particular topic, and it receives the message and can now respond accordingly. So let's jump back to the demo again and show a quick example of publish and subscribe. So again, I'm copying the same commands from the GitHub account, so you can follow along if you're looking to do that. So before I can publish and subscribe, I need to actually authorize the certificate to make that connection. So I'm going to start with getting a policy document from my account. This document has an allow clause for all of the IoT service on any resource. So you can take this same sort of policy and restrict it to different topics, restrict the certificate to what it can publish and subscribe to, and get as granular as you need to. For this case, we're going to keep a completely open policy document. I'm going to once again grab my certificates so I can quickly get the certificate ID of the last one I created. And then I'm going to attach this to the policy document. So I'm using the describe certificate call to grab the certificate that we already created. I'm outputting the text, and I'm going to capture the ARN, which is the Amazon resource name of this particular certificate. And I'll use this in the next command. So I'm taking this policy document that we showed first, the certificate here, and I'm going to attach the policy to that cert, causing the device to now have the permissions that are in that policy. Okay, so now this certificate and key pair can now publish and subscribe on any topics within AWS IoT. So on the left side, we're going to set up a subscriber. The subscriber is going to listen to an address that's assigned to my AWS IoT account. This is called my endpoint. This is my own dedicated front door for my AWS IoT account. I'm going to use the Mosquito subscribe command. I'm going to pass it the global certificate that we downloaded from the documentation, the certificate we created, and the key pair that was created through that first command we ran. I'm going to connect to my endpoint address using the standard MQTT port. I'm using a quality of service 1, and I'm going to use the topic lights, things, thing 1. and I'm also identifying myself as thing 1. So the subscriber is connected, he got the acknowledgement from the server, and now he's subscribed to this channel. On the right side of the screen, I'm going to use the mosquito publish command, use the same certificate pair, but I'm going to identify myself as control01, and I'm going to send the message, hello AWS IoT. So he connects, gets the connection acknowledgement, publishes, and then disconnects. On the left, we'll see here's the message that we sent. So it's important to note that I've identified myself as 2 different thing names, thing 1 on the left and control 1 on the right, using the same certificate pair. So that certificate key pair that we created can be used for an entire fleet if you identify the devices differently, or can be assigned to an individual device. All right, so that's a quick example of publish and subscribe. We'll get into more advanced use cases later on in the webinar. I'm going to return back to the slideshow. So the rules engine, like I said, it acts as a global subscriber for your messages. The rule defines what data you'd like to identify and what to do with that data when it is found. A rule has 4 basic parts. The name and the description are pretty self-explanatory. There's a part called the SQL statement, and there's an array of actions. So we use SQL because it's a familiar pattern for devices, and it's an easy way to describe a filtering mechanism. So this pattern is defined, and the actions dictate the response. So we're using a simple example here, select all from the things, thing to color topic, where color is red, but this can get pretty advanced. Both the filters and the actions are capable of a lot more. There's dozens of functions available to help with string manipulation, mathematical operations, cryptography, timestamping, and formatting templates. So you can query deep into the payload of a sensor message and be sure that the event is the right one to act upon. So let's take a closer look at a couple examples. So this is how the SQL statement is set up. You can look at the SQL clause within the rule that can be thought of as scanning a database table. So in our case, the default source is MQTT topics, but you can specify which protocol topic to analyze as the device gateway adds new protocol support. So wildcards are also supported for the topics in the SQL statement. Now the data clause, this allows you to extract specific elements from the MQTT payload. So the functions are designed for JSON. For non-JSON payloads, we provide patterns where you can process your data through a Lambda function and then republish it to another MQTT topic, where the rules engine can then act upon the JSON payload data. So operators exist to traverse multiple levels of JSON payloads. You can also apply functions to the payload and perform on-the-wire transformations. So for example, I could use a select as clause to rekey my data. Now this is a common use cases for devices that serve the same purpose but might have a different key. For example, one sensor might report temperature as temp and another one report temperature as temperature. So you can use functions like that to manipulate the strings, reevaluate the keys. You can use different functions to MD5 hash sensitive parts of the payload for some of the subscribers, or advanced substitution templates to completely manipulate the payload data and pull in other contextual elements. So all this is great when we're working with the data within AWS IoT. However, we understand that's not always the case. So we built a set of native integrations that you can invoke from the rules engine. So right now we have support for Lambda functions, piping data to an S3 bucket, publishing to an SNS topic or an endpoint, publishing to a Kinesis stream, to Kinesis Firehose, also republishing within AWS IoT to move data between topics. We have a special set of use cases for DynamoDB. So with Dynamo, you can query within context of the rule, pull data from a static table into the message payload, and you can also send to Dynamo for storage and analytics at the end of the rule evaluation. So in some cases, the machine doesn't have context of the human in its business environment. So consider a fleet example where there's a fleet management computer in a truck and there's a driver that might be from a different company. The rules engine can be used to query Dynamo to look up the driver's ID based on a routing table or schedule and inject the data back into the context of the sensor message. This could be used to secure data differently based on which driver's in the cab. It could also be used to route the message differently based on which contracting company the driver works for or the route to a different maintenance supplier, depending on which state the driver is currently located. So pulling context from DynamoDB has a lot of implications and advantages for your business applications. So let's take a look at a couple examples. First, Lambda. So Lambda is an event-driven compute framework where you don't have to pay for your idle time. It's used to execute your business applications functions in response to an event. So the rule we're showing here is looking for data over the topic things, rules, Lambda, and there's a function ARN. Again, an ARN is an Amazon resource name for the Lambda function. So this is the identifier for your particular Lambda function. Now this function could be your Java, your Python, or your Node.js application. So any message sent over this topic immediately invokes this Lambda function. So if you take a look at the Mosquito publish command, the same syntax we were using before in the command line, to send a message over the topic that the Lambda rule is evaluating, you can see that the payload color equals red shows up in the Lambda debugger under the event source. So streaming data is another popular pattern in telematics. If you're an application that's listening and analyzing the entire connected product fleet in aggregate, something like Kinesis is a great fit for consuming all of that data. You can set up a rule to filter out the noise, transform the payloads, and send data to Kinesis as an ordered stream for processing or consumption by the enterprise applications. Machine learning is another interesting use case for the rules engine. Amazon Machine Learning is available to model data and provide calculations and predictions. For IoT, customers can use AML to set up predictive thresholds in the rules engine, and then the rules engine in turn feeds data anomalies back to S3, where it can be reloaded into machine learning models to retrain and recalculate the predictions. So this pattern can be used to almost self-tune or recalibrate models over time within the rules engine. So one more sample use case before we go back to the demo of the rules engine. So device management and firmware upgrades are obviously important within IoT. So looking more broadly across AWS, you can quickly put together patterns to support firmware management for your devices. So you can upload the binary to S3. S3 triggers an event hook to a Lambda function. Your Lambda function can run your proprietary logic to decide how to distribute the update to the field. At this point, you can decide even to work across multiple regions. So you can publish a pointer to the S3 file location, and then the rules engine will track responses and store the progress of the updates in DynamoDB. So maybe this even updates the versions automatically in the device registry. The key point here is that the building blocks are available to handle these scenarios. So we're going to take a look at this rule in action. So this rule looks at the things, rules, Dynamo topic, and it saves every message to DynamoDB. So there's a couple key things to call out. The fields have to match the fields that you defined when you created the Dynamo table. So we assume you already gave the rules engine permissions to execute the Dynamo actions in your account. So this was done with the policy document we looked at earlier. Now you can read more about that in the developer's guide. Now within the rule, notice the orange values. These are string substitution templates that the rules engine will evaluate on the live message. So the hash key value will receive the third element of the MQTT topic structure. In this case, it's always going to be Dynamo. The range key value will get a timestamp. All right, let's take a look at how this works. So I'm going to log into Dynamo real quick. I have an empty table called AWS IoT. There's currently no elements. I'm going to set up a subscriber to listen to my rules. Again, I'm identifying myself as thing 1. I'm listening to the pound topic, which is a global wildcard for all MQTT topics. So I'll be able to see all traffic coming in. Let's quickly take a look at that rule, make sure it's the same as the one we defined. So now I'm looking at things, rules, Dynamo. The rule is substituting the third element of the topic array. It's also creating the timestamp, and it will inject the data into the Dynamo AWS IoT table. So let's go ahead and publish a sample message using Mosquito. So I'm using the same certificate pair. I'm identifying myself as control 1. And I'm going to send color red as a JSON payload to the topic the Dynamo rule is watching. So we're going to connect. We've got the publish. We've got the publish acknowledgement. And on the left side here, we can see the subscription that picked up the JSON. So if I return to the Dynamo console and refresh, we'll see the element that came through and the payload from the JSON array. So you can also notice that the topic variable now has the static string Dynamo, which we pulled from the MQTT topic. And the timestamp also injected the current time of the message. All right, so we sent a series of messages, 3 in total before we got disconnected. One of them, we were using a duplicate client ID. So the subscriber was forced disconnected and reconnected on his own. So we should see 3 total messages in Dynamo now, each with the same JSON payload. All right, so we're going to talk about the device shadow next. So the shadow, as I mentioned, is a logical interface for your physical product. It gives the web or mobile application developer a way to interact with the device over a REST API, regardless of the protocol the device is using to communicate. So the abstraction between the protocols is all handled by AWS IoT. So here's how this works. So the device, whether it's using RSDK or an open source standard client, can communicate its state to the shadow topic. The state is stored and is always available to the API. A companion mobile app, for example, might query the state of the device when it loads the welcome screen. So take the example of a connected vacuum in your home. The mobile app for your vacuum needs to know if the device was last reported running or docked, or if the bin was full. So at any time, the device or the app can request a change in the desired state of the device. For example, we might request to turn the vacuum on or off. The shadow negotiates the difference between the desired state and the last reported state of the device, and it broadcasts just the delta to the connected device. So now the device can choose to change its state, acknowledge the change in state, or error on the request. So whatever the outcome, the shadow communicates the results back to the application so that everything remains in sync. So it's important to note that in some cases the device is not currently online during this exchange. So in that case, the shadow will continue to negotiate the deltas and deliver only the last valid version to the device when it reconnects. So the shadow does not require a change to the way that devices are working already. This is a complementary feature that works alongside your normal topic structure. So we've introduced a new topic space, $AWS, to handle internal operations, including those performed by the shadow. So all operations, updates, deltas are all broadcast over MQTT topics. So you can create rules on these topics to do things like trigger functions and state changes. You can create a rule at the global things asterisk shadow topic and send everything to Kinesis to maintain an ordered stream of all state changes globally across your fleet. So there's lots of potential here. So let's take a look at how the shadow works, going back to the AWS CLI. All right, so first we're going to look at the registry and we're going to describe, let me just clear these up. We're going to describe the metadata around thing 1. This is what we'll use to demonstrate the shadow. So here's the thing 1. Here's the attributes that we looked at in the screenshot of the console earlier on. We're going to use this one to manipulate state. So let's go ahead and get the current state of the shadow. So I'm using the command get thing shadow and passing the thing name, and then I'm piping the output to a tool that formats JSON so it's easily readable. The CLI command ends with the thing 1. So this current shadow has a state. So I'm going to go ahead and null this out so we can start from scratch. So to clear a shadow, I can send a publish command using the Mosquito publish utility, pass it the same cert, identify myself, and publish to the AWS thing 1 shadow update topic. So now I'm going to set the state to null, which will clear all the different parts of the shadow. So if I go back and take a look at the shadow again, now my metadata and my state have been cleared, so we can start fresh. So I'm going to set up a subscriber to listen to all the commands that the Shadow is receiving and acting upon. So I've connected on the left part of the screen to the thing topic, the Shadow for that particular thing, and then the wildcard. So this will pick up everything that was acknowledged, errored, and the Delta channel. So let's start by publishing a Shadow state of red. So I'm sending a JSON document that says my state currently reported is the color red. This gets published over MQTT. On the left, I can see the subscription get picked up from the Shadow topic. And if I go back and requery my Shadow state, I can see that my last reported value is the color red. My timestamp's been updated, and the version of the Shadow document has been incremented. So if I'm going to go ahead and change the reported state to green. Using the same publish command, but now the JSON document says color green. And then we'll once again check the thing shadow. Now the reported state is green. So this is great for kind of reporting the current state of the device. If I want to update the thing shadow from a different application, I can use the AWS CLI command update thing shadow and send it the payload of the desired state. So now we have our state element only shows reported. Let's go ahead and send it the desired state of red. So this will flip from what's currently reported as green to a desired state of red. The shadow has calculated that there's a delta indicating the device should flip its color to red. So over this entire time, the subscriber has been listening to the different transactions. We can see a bunch of different messages come through. All the state changes have been processed. We can see when we flip from green to red. And then we can notice that on some of these, there's been accepted changes. So if you look at this topic here, the shadow update has an accepted change of its desired state to red. At the same time, just the delta was published over the delta channel. So now if I'm a device and I want to minimize the amount of traffic that I'm receiving and processing, I can listen to just this topic as a subscriber. So I'm going to go back and report that as a device, I've flipped my current reported state from green to red, which should match the shadow desired state, removing any delta in the difference. So one more time, we'll get the shadow. We'll see now I have a desired state of red, I have a reported state of red, and the delta element is no longer present. So the shadow is currently in sync. Here's the last timestamp of a desired change, the last reported change, and now my version number has been incremented one more time. So throughout this process, the application developer and the device can negotiate how to change states and keep current between them. So that was the shadow. Let's quickly talk about pricing, and then we're going to go through the hardware and SDKs. So we've gone through most of the getting started experience so far. We've covered quite a bit of content. So let's quickly discuss the pricing and hardware ecosystem. Pricing is pretty straightforward. It's based on messages published to or delivered from AWS IoT. So we don't charge for features like rules, shadows, or current features that are present in the registry. We also don't charge for delivery to other native AWS services that are defined in the rules engine. So for example, if you publish a message, there's a subscriber to the message, and that rule delivers it to Dynamo as well, you'll be charged for two messages, one for the publish and one for the subscriber. The third delivery to Dynamo does not incur any charges. So there's also a free tier. You can read more about that and other pricing elements on the website. So IoT is a lot about the ecosystem. We've started with a core set of open source SDKs. In addition to the standard AWS SDKs, these device-specific SDKs provide wrappers around open source MQTT clients, like the PAHO client from the Eclipse Foundation. We've also found a series of fantastic hardware partners who built kits designed specifically for AWS IoT. So all these kits come with the Getting Started tutorials. They each have, each kit has a specific and unique purpose and theme. And some of these kits and the SDKs have porting guidelines, Some use the AWS SDK, others use the vendor-specific libraries. So it's a broad initial portfolio that will help you get connected quickly. So in summary, we've talked about the different components of AWS IoT. We've created a certificate and a private key pair to identify and secure a device. We've used that to connect and publish over MQTT to the device gateway. We've set up some rules and actions, sent some sensor data directly to Dynamo through a rule, and we've experimented with state changes using the device shadow. So we went through the pricing and covered the SDK and the hardware kits. So I think we're going to move to some Q&A, and looks like there's quite a bit of that. So on the left side, you should also see some questions. So if we can get through the survey as well, that'd be great. So, all right, so one of the questions from the room is how do you embed certificates into a device, which we created earlier? So the idea is that this command is executed over a secure connection. It uses your AWS IAM credentials. We'll pass you the private key and the certificate over that connection, and the expectation is that you can capture that and move it to the device however you sort of interact with devices today. So you would, you could execute this from something like a Raspberry Pi that's capable of making that type of connection, or maybe the machine or the HSM is connecting to a lower class sort of constrained environment, and you would transfer that over serial or something like that. So once that key is transferred over the wire, it doesn't exist any longer on AWS IoT, so you have to recreate it if you lose that key. All right, so another question is it possible to store a JSON object in DynamoDB using the rules engine? So it looks like it parses and stores it as a map. Do I need to store it in S3 and then process it later? There are string manipulation templates available with the rules engine. We can go through some more of those examples and make sure the documentation covers that. So you can manipulate both the payload and how we process it. So does the device maintain a persistent connection with the IoT service, and how does this work over HTTPS? So persistent connections today can be done over MQTT. HTTP is a request response. All the actions over HTTP will result in an MQTT publish. As we add WebSocket support, those will also be persistent connections. With HTTP, we would have to eventually look at things like HTTP2 to keep that connection open. But yeah, right now HTTP is request response. MQTT in the coming feature for WebSockets will provide the persistent connection. So is there a way to disable device shadows for creating things like, for certain things like door locks? So shadows are interesting. They work alongside your device, right? So you can put rules in place on top of the shadow topics, decide how you want to deliver that to a door lock. They're in no way a requirement. So if you wanted to have an extra layer of security or logic around how the shadow was to behave, you could use the rules engine to intercept that sort of message change before passing it on to the physical device. All right. So another question is, how can an application check if a device is connected or disconnected? So different events in the system key MQTT messages, and you can process rules based on those. You can also use CloudWatch logs and metrics to check sort of current actions within the system. Is there a couple more? So the minimum payload size the service supports is another question from the room. So it's basically any payload that you define. So you can send as small of a payload as it makes sense. So there's a question about any advantage or disadvantage of using a Raspberry Pi over an Arduino. In respect to the service, there's not much difference at all. The minimum security requirement for connection is TLS, mutual authentication. So with Arduino, the upper class Arduino devices like Yun and Zero would be supported, but something like an Uno would have trouble making a TLS connection. Raspberry Pi, on the other hand, would have no problem either way. So for proximal network protocols, there's a question about whether or not a gateway would be needed. So right now the SDK is built as a proxy to the proximal environment. So you would set up the SDK on a gateway, bridging to whatever sort of antennas were present there, proxying the information over MQTT or some other channel back to the cloud. So for that particular question, yeah, you need to use the SDK to proxy that information. Okay, so the question, the next one in the room is, can you explain how the AWS MQTT server works with Lambdas to invoke other AWS services? So we had a whole set of integrations that we talked about, from S3 to Kinesis to Firehose to Dynamo to Lambda. From Lambda specifically, it's pretty easy to jump out to any of the other AWS services. You can execute your Lambda function at the end of a rule. So I can evaluate things like find the devices that are sending messages where my oil pressure has exceeded a certain amount, and then those payloads will be sent over to Lambda. Lambda can parse them, do what it likes, and pass it to other AWS services. So there's another question. If HTTP is request response, are we using polling in the client for bidirectional messaging? So if your client is strictly based on HTTP, then right now you would be polling to the shadow topic for state changes. You would publish to an HTTP command that would broadcast an MQTT or WebSocket message in response. So the next question is, how do we restrict access to the device shadow? So all topic spaces are restrictable through policy documents. So we can create as granular security sort of schemes as needed to make sure that only valid subscribers can listen to the device shadow or publish to that topic.
I just posted a link on the docs.
Okay. Yeah, for the maximum payload size, we posted a link to the document in the chat room. So is there any advantage to using the IoT rules engine versus plain Lambda? So there's a couple advantages. So if you look at the IoT rules engine, it works in context of the publish-subscribe system. So you can start to evaluate and manipulate data over aggregate topics. So Lambda would be used at the edge of the execution. So I can start to identify patterns that are happening over one topic or multiple topics and send to Lambda. The rules engine can do things like basic transformations, calculations, reformatting of messages, republishing to other topics for sort of a daisy chain rule effect. So there's a lot you can do with the rules engine before you send it to something like Lambda or Kinesis for post-processing. I think we can capture those. New question is there a comparison between different hardware kits available and the pros and cons of each? So yeah, all of them have sort of a description on the website. You can look at kind of the purpose of that kit. Some of the ones are focused on different themes, like maybe environmental sensing. Some have a connected car example. Some of them are using other antennas, like the Broadcom AvNet kit uses a Bluetooth low energy antenna to proxy information back to the cloud. So each one has its separate sort of unique advantage and purpose, and all the descriptions are available on the website. Okay, so new question is, do I need to write my own logic or rules if I want to store historical data? And is there a side effect of simply sending data? So this is actually this is a great question. So we've decided to put this back in the hands of the user. So any sensor data you want to store to Dynamo takes a simple rule, and then we'll funnel all of that data to Dynamo, you can store it as long as you need to. So what we didn't want to do is make decisions on how long your application would want to store and prune data. So that's completely under your control. You can send everything or nothing for storage. So the side effect of simply sending all the data would just be the Dynamo costs. So we don't charge for transport to Dynamo, but you would be charged Dynamo storage fees. So if I lose a connection from the device and the shadow is updated during the lost connection, on reconnection of the device has to resubscribe. Will this include the event that happened during the lost connection? So if your device is offline and your shadow is updated and there's a delta in the state and you reconnect with the subscription to your shadow, you'll get the last valid change of state for the shadow. So for example, if I was offline for a couple minutes and there was 50, 60 state changes on, off, on, off, on, off, when I reconnected, I'd get the last valid change so I would know how to respond. So the next question is there a Java API for using Android as a sensor device? So Android and iOS SDKs are being released shortly. So those are in active testing. So you'll be able to use Android as a connected device. The next one is, does the SDK provide a way to update device firmware securely? So firmware is interesting. A lot of it depends on kind of the capabilities of the device. What we've put together so far is a pattern where you can manage your firmware update process within context of AWS. So the example we talked about earlier, I could put my firmware update in S3 that would trigger a function that cascades sort of an MQTT publish with a link back to that document. The device could download it, publish over a different topic, and we could track which devices were updated in Dynamo. So it would take a set of rules to do that. All of that would happen securely, obviously, within context of your policies and the rules that you defined. So the last one is there a limit to the size of the data you can store in the shadow, and is there a recommended best practice? So the first piece is there's an 8K document limit for the shadow, so you can have an 8K JSON doc. We'll calculate differences and deltas at every level. So that's quite a bit of information to keep for sensor data. The recommendation and best practice, it's all over the place right now on how people are using the shadow. So we've seen folks use it to make a one-to-one mapping from a physical product to a shadow. We've also seen the shadow being used as a logical grouping of a set of devices. So if you're back into the connected home example, I could have a shadow for each of my appliances, but I could also have a shadow that represented the entire state of the house. So yeah, lots of different use cases are emerging. All of them seem pretty relevant. Great. Okay, well, thanks everyone for the time.
I'd like to extend a special thank you to Kyle for his time and a great presentation, and also for audience making all the great questions, and our moderators, Chetan Dennerkarn, Ian Rasmussen, John Burry, John Terrell, Katie Stackman, Mark Ralph, and Oliver Schoen for facilitating questions throughout the presentation. So sorry that if we cannot get to your questions, but we will follow up to all the audience with the link to the recording as well as the deck. So if you have any comments on our previous and upcoming webinars or suggestions on any topics you wish AWS may cover in our future webinars, please feel free to email to aws-webcasts@amazon.com. Again, it is aws-webcasts@amazon.com. Your feedback helps improve our webinar programming. Thank you for taking the time to join us today. Enjoy the rest of your day.